Hello everybody. Today we are going to talk about the third recursive recurrence method, that is the master method, and we are going to solve the same equation that we have solved in our previous videos using recursive iterative method, substitution iterative method and recursive tree method. So we are going to solve it using the master method. So what is the master method? Master method depends upon the following theorem, which assumes that let a be greater than equal to 1 and b greater than 1 be constants from this equation, and f of n be a function. So t of n, this is defined by a non-negative integer. So t of n is equal to a multiplied by t n upon b plus f of n, where n upon b needs to be some floor or ceil value. That is, you don't need a point value in this ratio n upon b, it has to be some sort of a whole number. So if these conditions are met, what do? We have three asymptotic relationships that the master theorem gives us in three equations. First equation is if f of n is equal to big O log of n log b a minus epsilon, where epsilon greater than 0, then t of n function is equal to theta n log b a. So if this equation is satisfied, then t of n should be equal to this. That is it. We'll solve when we'll understand it better when we solve it using the numericals. So the second equation is if f of n is equal to theta n log b a minus epsilon, then t of n is equal to theta n log b a log of n. This is the second equation. And the third equation is if f of n is equal to big omega n log b a plus epsilon for some constant epsilon greater than 0, if a multiplied by f n upon b is less than some constant multiplied by a function, where constant should be less than 1 and n should be sufficiently large, then we have t of n is equal to theta f of n. So these are the three equations of Master's theorem if these assumptions are satisfied. So let's look at them and try to solve them with our given equation. Again, this is the same equation that we used for solving the substitution iterative method in our previous video, as well as recursive tree method in our previous video, right? So let's take this equation. So when we take this equation and put it in our form, we get what? A is equal to 2, b is equal to 2, f of n is equal to n square, and we can calculate that log b a is equal to log 2 to the power log base to 2, which is equal to 1, right? And all the three equations of the master method are written here mathematically. You can see over here, this is equation number 1. If that is, if function is equal to this, a function of big O is equal to this, then we can have t of n is equal to theta of this, and so on. So let's first solve equation number 1. So equation number 1 is this: f of 1 is equal to big O and log ba minus epsilon. So we have already calculated that log b of a in this particular equation becomes 1 minus epsilon. If we replace the epsilon with 3, because epsilon can be greater than 0, we get what? N square is equal to big O n square. So this can be true. Let's verify. So we place it in the t of n. T of n is equal to theta n log b to the power a, and we get what? Theta of n. So if big O is the upper bound, that is it is going outside the boundary, theta has to be between the big O and the big omega, which means that on the graph or asymptotically, theta value has to be smaller than the big O value, which is over here true. Hence equation 1 holds true for master theorem for this particular equation, right? Because it is asymptotically tight. Let's try to see whether equation 2 and 3 also hold true or not. So for equation 2, that is this one, for equation 2 we have to verify the theta value. Theta value n log b a minus epsilon is equal to theta n to the power 1 minus epsilon. Epsilon can be 3, and we can get n square is equal to theta n square. Okay, seems like it can be asymptotically tight. So let's verify. Once we verify, we get what? We place the values in this equation, that is theta n log b a to log of n, and we get theta is equal to n log of n. Here we have a problem. How? we cannot have, because these are not equal. Theta n square is not equal to theta n log of n. These two are not equal. Hence it is not asymptotically tight, and equation 2 does not hold true. The master method equation 2 does not hold true for the given equation, for the given problem. Okay. Similarly, let's verify it with equation number 3. Equation number 3, we have big omega and log ba plus epsilon, and we can solve it. And then we have epsilon is equal to 1. We get what? N square is equal to big omega n square. Fine. Let's see if we can verify it. So T of n is equal to theta f of n. Okay, theta f of n is equal to n square, which is not true. How? Big omega is equal to n square, theta is equal to n square. Big omega is the lowest bound, that is just like big O, which gives you the upper bound, big omega gives you the lower bound. Theta is supposed to be higher than the big omega, but over here theta is equal to big omega, which is not true. Hence it is not asymptotically tight, and equation number 3 of master method also does not hold true for the given problem. So in this video we have proved that the master method for this particular given problem, the master method equation number 1 holds true, whereas master method's equation number 2 and equation number 3 does not hold true. I hope you like my video. Thank you very much. Kindly subscribe.